advantage of HPC resources with concurrency and process parallelism. And then finally, we'll look at some important job submission parameters that you'll want to look at when you're using multiprocessing with Python. All right, so first off, Python's a programming language. And like most languages, it has some properties that make it unique. It's a very popular language for modern researchers and programmers. And that's likely because it's very broad in its application as a general purpose language. It was designed for readability. That is, it doesn't really look like some cryptic blob of pointers and special characters when you look at the code. And it's also very portable, meaning, if you run it on Linux, you can with relative ease move it into a Windows or Mac OS environment and run the same code. And the way it does this, it's a high-level object-oriented language, but the way it's portable is it uses an interpreter. So the interpreter sort of sits in the middle of, in between the Python code itself and the operating system, and it translates the Python code into machine code or something that's more understandable by the operating system. And so there's no compiling required. You can write the code and run the code using the interpreter. Additionally, there are just tons of different libraries available to use. Python lets you extend the functionality very quickly. But the one thing you don't usually see when discussing the benefits of Python is performance. That's okay because there are definitely ways to boost performance, and we'll talk about some of those ways today. And here are just a few other reasons we see Python used so much within the research community, just the sheer number of libraries available, scientific libraries, data science, providing simple interfaces to do, to get work done. There's a lot of applications for machine learning, artificial intelligence, and GPU libraries that you can use. And then, of course, we'll talk today mostly about multiprocessing. There are some multiprocessing capabilities that sort of started finding their way into the core Python distributions about version 2.6 forward. All right, so what some of you may be used to when you're working with Python is developing or running things on your local workstation. And when you're doing that, you don't have to worry a whole lot about permissions issues or being able to change certain paths. You may not even have to really do much of that at all in general. You have administrative control, usually, at least some semblance of administrative control on your local workstation, whereas on a shared environment like HPC, you don't have that system level control. And so that's probably the main difference between what you're used to working with in your test environments and versus what you get on HPC cluster. You also probably don't have a whole lot of, you have libraries installed or packages installed that are real specific to your workload. So you have a minimal number of libraries available for use. Whereas on HPC cluster, the globally available versions of Python are going to have all sorts of different modules installed. And that can sometimes lead to conflicts or just kind of difficulties along the way. So that's another big difference. Again, you're going to have workload specific. I got my lines mixed up there. I think the versions, what I'm talking about there is you might have a version 3.6 that you use all the time, whereas on HPC you can load, 2.7, 3.6, 3.9, all sorts of different versions available. And then, as discussed, usually a minimal number of packages and libraries on your local workstation, whereas on the cluster you have lots. And then your environment settings, you probably don't have to mess with them too much when you're working in a test environment or a specific use environment on your workstation. Whereas on HPC cluster, you have to kind of manipulate those environment settings in order to tell the system which particular version of Python you're using, where your packages are installed and things like that. And so what those environment variables allow you to do is to specify the locations. Where's your Python interpreter located? Where are the libraries located that I need to search for? And the main ones that are Python related, the first one being this path. And so the path environment variable tells the operating system where to look for executable programs. A couple of other ones that are actual Python environment variables, not operating system environment variables, are the Python path and Python home. And those, again, sort of can be used to manipulate where to tell the interpreter to look for certain packages or libraries. So an example, let's for example, take a look at the path environment variable. The way you do that is with this echo statement. And then you have the $ and the name of the environment variable, which the environment variables are usually all uppercase. So in this case, we're going to say echo $path, which should give us the current value of the path environment variable. So most of the time when you do that, you're going to see a very standard list. And this is a colon delimited list of all the locations that the operating system will look to discover executables, binaries, programs that can actually be run. So we're not talking about data files in that case. We're talking about, the Python interpreter, for example. So if we issue this command, which Python on a Linux system, that will tell you where the location of the Python interpreter is based on your current environment settings. In this case, a lot of times by default, you're going to get the default system Python interpreter, which is in user bin. And if you really wanted to further confirm what version you're using, you can use this -v or -- version, and that'll show you, okay, this is actually pointing, when I run Python, the version is 2.7.5. So we can ask the interpreter what version it is, and it's going to return this. But what happens if we go ahead and manipulate that path environment variable so that we have this extra path sort of prep-ended to the list? And you can see here that's done with this export command. And you see in this case, we're not using the $. We're actually issuing the name of the environment variable without the $ and saying equal to, giving it a path, and then there's that colon. And then we refer to the $path, which is saying basically prep in /tools/python -3.8.6 to the existing value that's in the path environment variable. And when that returns, you really don't get any output, but you can assume if the output is empty, that the command has been successful. If you wanted to actually confirm that, you can now issue the which Python command again. And now you see it's actually pointing to an interpreter that's located down in the tools directory. And just to further confirm, we can issue the version command again for the test. And now we see that the version is 3.8.6. So just a quick look at the path environment variable and how you can manipulate that to point to certain versions of the interpreter. All right, so let's take a look at the other two we mentioned, which are the Python path and Python home. So in this case, what we're doing is we're just running an interactive shell into the Python interpreter. And so if you type just Python on the command line, it'll drop you into this sort of shell looking environment where you can issue language commands, language functions, and things like that. In this case, what we're doing is trying to import a module named mod. This is just sort of a arbitrary module. And what it's telling us is that there is no module named mod. So what can we do to work around that? Well, again, we'll use an environment variable. This time it's a Python specific environment variable called Python path. And we're going to tell it, look in this directory home/home/HPC user/Python. And we're not even prep-ending the value. We're just changing it all together. So this is setting it to just this single location. And once again, when we do that, we'll get an empty, if it's successful, we'll get an empty result. Then once we've changed that environment variable, if we issue the interpreter command again into the interactive shell, we can run this import mod, and now there's no error. And then on the line below, just to be sure, we can use this dot, and it's a really strange looking property or variable, but there's __ file, and then 2 more underscores, and that shows the location. In this case, there's a bit of a typo here. This is my home directory, but it should say home HPC user Python custom. So that's just an example of how to manipulate those environment variables. And those are the ones that are going to be mostly of interest when you're trying to adjust for your workload on one of the HPC clusters. But fortunately, we have module files. So that gives you a little bit of an idea what goes on under the hood, but module files will take care of a lot of that for you. What you can do with module files is, first of all, find the existing versions of Python that are available on a cluster. You can load the modules to adjust your environment to use those specific versions or a specific version. And then you can also switch them around, and you can see there are certain commands that will show you what's going on beneath the surface and what it does to your environment. So for instance, module avail Python will give you a list of all the available versions of Python in the cluster. If you use a module load with this syntax, it will actually set your environment to use a specific version. So in this case, it's a module load Python. There's an optional value in the middle, which is the distribution. And most of the time you're going to see something like Anaconda. So Python/Anaconda in the version. And then if you wanted to actually see what it's doing and how it's manipulating the environment, you can use a module show with this sort of similar syntax there, an optional distribution in the middle. So just to demonstrate that real quick, module avail Python, list all the globally available instances of Python. For instance, this would be on Easily, the Easily cluster, and you can see there are a number of versions listed. The L next to a version means that that's the version you currently have loaded. And if you see a D next to that version, that's the default version. So here I'm saying, all right, I want to load the Python version 3.9.2. And it's telling me, okay, I had 3.8.6 loaded, and now I'm replacing that with a newer version. If you don't have any existing Python module loaded, the command should probably just return with no output, and you can check that with a module list to see what's currently loaded for your environment. All right, so here's where we'll take a look at what's actually happening in terms of the environment variables. If you do a module show, and then whatever module version you want to look at, it should show the details of what's going on behind the scenes, including any source commands. And there's more in the output than this. It's just sort of truncated it for this presentation. But you can see where it's doing these prep in statements to manipulate the environment variables we previously talked about, both Python path and Python path. You also see the LD library path and library path environment variables, and those are often set as well, just so that the operating system knows where to get to more core type shared object files and libraries. So that's a quick look at both the sort of standard or more closer to the machine way of manipulating the environment variables, and also doing that with module files and how you can see what's going on. Okay, so that's all nice. We can manipulate things so that we know what version of Python we're using, use specific versions, and set different locations for libraries and packages. But how do we get around the issue where we'd like to install some custom modules, but we don't have access rights to do that into the system locations? And so that's what virtual environments help with. What that is a context-based control of library installation, or just really a Python environment in general. And when I say context-based control, it means really in the context of the user and the privileges under which you're running. So it's a workaround to basically shift the location of packages or anything writable into a location to which you have access to write. Most of the time, that's going to be your home directory. Sometimes you might be able to do that in something like Scratch, but it works around the fact that you're not going to have write access to the vast majority of locations in /tools or in the root file system. You can also create multiple virtual environments for specific workflows. If you have several different experiments you're running, for example, you might create an environment for one and that uses a specific set of libraries, specific versions of libraries, and another one that uses a different set. And there are also a number of research benefits to using virtual environments. It's good for benchmarking. So, and this is really all just related to consistency. If you create a virtual environment, it's sort of a self-documenting way to know exactly what versions and what libraries and what your environment looked like when you ran these experiments, so that you can duplicate it relatively easily. You can tar up that virtual environment and distribute it to colleagues or whoever who want, if they want to validate your experiments or whatever the case. And it's good for documentation. So virtual environments are really, they've become really sort of our recommended way for, if you're doing a lot of Python work, you have a lot of Python workloads, this is really our recommended way to go about it. So some of the common tools that you can use, and we speak really just two core implementations, I guess you could say. One using the standard Python, and that really shouldn't even say pip. It's there are a couple of pip commands, but the actual creation of the virtual environment is done with the standard Python interpreter. Or some people may use Anaconda. The Anaconda distribution is really sort of it includes Python, but it's a much more broad distribution. It's a data science environment. So a lot of people that do a lot of data analytics type things will use Anaconda because it has a lot of the tools built in. It actually has an R distribution for statistics. So it has both R and Python. And that's really the main difference between the standard Python and Anaconda is just the way it's distributed and what packages are included. But they also provide some nice tools like the Conda tool, which you can use to create the virtual environments if you're using that particular distribution. The general way it goes about doing this is it says, okay, I'm gonna copy the core files, the essential files from a reference version of Python that I can see somewhere. I'm gonna copy that stuff into a place that's writable. And then I'm gonna change the environment settings to reflect where I've moved that content into the context specific or user specific path. So just a quick run through on that. In this case, we're using the standard Python. So we're going to change to our home directory first, and we're going to load the default version of Python. In this case, I believe it was 3.9.2. And when you're using the standard Python, it's good practice to go ahead and create, some sort of directory or a folder to hold your environments. And so in this case, we're just going to create one HPC ins, and then we're going to move into that directory. So here we're using the Python interpreter. That's the Python command you see first there. And there's a -m, which basically says, okay, search for the module called virtual env and then run any associated script. There might be a .py script associated with that module. Run that script, and what that script in this case will do is going to create the virtual environment in a new directory called HPC1, which is in that higher level directory HPC-ims. And you can see just the highlighted output there. It says, okay, I've created that. I've copied some things into that home HPC user HPC-ims directory. And then I've also copied some things into this .local directory inside the user's home directory as well. .local is sort of a shared location that a lot of different programs might use to just dump some state information or environment information, and it'll refer to that sort of implicitly. So if we take a look in the folder after we run this command, if we take a look in that HPC1 folder, we should see that it's created a bin directory, a live directory, and then a config file. And those are the essential files. Inside bin, you'll have the Python interpreter. So you'll have a local copy or a copy of the Python interpreter, your home directory, and then the live directory, it's going to look a lot like the standard Python live directory, but probably a lot less files there. It's just going to copy by default the essential ones. And the way that you actually activate a virtual environment. So now that you've created it, you have to tell the system, okay, I want to actually shift my context into this virtual environment. And for standard Python, you can use something like this: source, and then the location of the bin folder, the name of the environment, the bin folder, and then there's an activate script. When you run this command, it's going to actually run the contents of this activate script. And if you wanted to really take a look, you could go and just cat the contents of that file. It'll show you what it's doing. And you'll see that when you do that, the prompt changes. Usually the prompt will change to show you, hey, I've got this, in parentheses, HPC1, and that lets us know that we're actually in the context of a virtual environment. So just to run through real quick, the Anaconda version of that, in this case, it's pretty much the same thing, except we don't have to create a directory because Anaconda is just going to copy things into a location in the home directory .conda. But what we do have to do is issue this export command to tell it that we're using a different location for the packages. If you try to run this command here, conda create new environment HPC2, without setting that conda packages directory, you're going to get an error on permissions. It'll say, I don't have right access to create the folders I need inside the packages. So that second command there is really important, but you don't have to create directories. You just run this conda create, and then it'll go through and create that new environment, virtual environment for you. And here you can see the location. That's where it's dropped everything in your home directory .conda, and then there's an ims folder and whatever name you've chosen for the environment. Very similar to the previous one, except this time you really just you don't have to give it a full path. You say source, activate, and whatever the name of the environment is, and it'll drop you into a very similar looking prompt to let you know that you have entered the virtual environment. Okay, so that covers sort of manipulating your Python environment so that you have one, control over what interpreter you're using, and two, control over the location of the packages, and then three, ensuring that you have the necessary privileges and file access rights in order to install new packages and do things like that. So now we'll get started on probably the more technical part of the presentation, and we'll talk a little bit about concurrency and parallelization for Python. I'll just start with sort of the, I guess, brute force, or I guess really coarse-grained way of parallelizing some of your workflows, and that would be through data segmentation. So the way that a lot of times traditionally you might go about it is that you have some sort of large data set that you want to operate on, and rather than just using a single process or a single job to perform whatever calculations on that data set, you might break it up into what I say are non-dependent blocks. So meaning, you can perform those calculations independent of one another. And then once you've broken that up into the appropriate chunks or blocks, you can execute multiple jobs all in parallel in order to perform their sort of local, it's quote unquote local calculations, and then do some sort of post-processing to combine the results, or I guess the word they use is to reduce the results into the actual aggregate calculation. There are also some various libraries and implementations for MPI within Python. The main one I think is MPI for Pi, which I have tested a little bit and it seems to work okay. But we're not going to really delve too far into that today, just because those can get really technical really quick, because you really have to, that's more of a discussion on MPI programming. And a lot of the things you'll use with these implementations are going to be very similar to what you do in C++ or everything else. You have to know the name of the different various MPI functions and how to call them and things like that. So what we're going to focus on today is multi-threading and multiprocessing. So threads versus processes. The recommendation, according to most of the documents, including the Python documentation, for when to use threading and when to use actual parallel processes is based on the target workload. So if you have something that is IO bound, meaning it's bound for the file system, or you're doing some kind of API calls, basically anything where you're having to communicate with some device or endpoint where you're having to wait, that would indicate an IO bound workload. And that's when you're going to want to use threading. Now, if you're just doing math operations and everything is really just calculations, you're probably going to be better off using a process-based parallelization. And I have here indicated the type. So you have thread, which is concurrent, and processes, which are parallel. Concurrency really means that there's some overlap within a specified time frame. You're not really necessarily doing things exactly at the same moment, but there is some sort of opportunity or waiting that the operating system can detect and issue a thread request so that you can get a little bit of overlap between processes. And then parallel, what I'm saying there is those are calculations that are happening at the same moment. Now, threading with Python really only uses a single core. So it doesn't matter if you've requested 48 cores from machine. If you're using threading, it's all going to sort of be bound for the same CPU core, whereas processes are all going to be allocated to specific cores. So the examples, like I mentioned, for threading, file system operations, API calls, or for processes, math operations. So this is just to further the kind of the concept of threading. Let's say you had some operation here that's a request. Let's say it's a request for an API call or something like that. Well, in a traditional serial fashion, you're going to have to wait. Okay, request 1 goes, it completes. Request 2, request 3, and you're going to have to wait all this time for each request to complete. But what if you did this and got some sort of overlap to make things more efficient? And so what it would look like is something like this. Request 1 kicks off, and then, hey, the operating system detects that you're waiting, and so it's able to go ahead and spin up a new thread and kick off the second request while it's waiting for request 1. And so you get that concurrency. You can see there's overlap, but they're not actually happening, at the exact same moment. So that does improve your efficiency. Now for process parallelism, this is a much more sort of self-explanatory diagram. You're doing calculation 1, 2, and 3. You have to wait for 1 to complete before you do the second and the third. But because you've got multiple cores and you can allocate processes to each core, you can do those things in actual parallel fashion. And you can oftentimes get a linear speed up depending on how your calculations are performed. So hopefully that conceptually sort of illustrates the difference between threading and parallel, and also highlights when you want to use each. All right, so for multiprocessing, in version 2.6, Python made the multiprocessing library part of its core distribution, and it's the sort of older way to do things. All these functions are still available in the newer versions, but it's a little bit more complicated as far as your coding. You're working a little bit more at a lower level than what they've introduced as a version 3.2, which are the concurrent futures interface. And that's just sort of a higher level interface that's supposed to make things a little bit more intuitive for using threading or multiprocessing. So an example of threading using this concurrent futures library looks something like this. You're going to have a thread pool executor, and then you're going to indicate however many threads that you want to use. So you tell the Python interpreter to initialize this thread pool with a certain number of threads, and it's going to return an executor object. And then with that executor object, you can go ahead and loop through. In this case, we're telling the executor object to call some sort of IO bound arbitrary function with, we're passing it parameter 1, and then we're going to assign an item in a predefined list. In this case, we just have sort of a real basic array. And we're going to iterate through that list, and then as each thread is completed, we can do things with the result from that thread. In this case, we're just printing it, and so that's really all that's needed to do threading there. But even more simplistic is with process pools. So this is the process version, and here we're doing very similar. We're saying, hey, with this library, we're going to use a process pool with a number of workers, return the executor object. And it gets a little bit more complicated because you have these zip and map functions here. The map method is to break whatever you've provided as input into chunks based on the number of processes. You can specify the chunk size with an extra parameter, but by default, I think Python does a pretty good version of divvying that up according to the number of cores you have available. And then this zip function is really just to kind of pair the number, the input value with the result. So this was pulled from the Python documentation, modified slightly from the Python documentation at the URL listed below. So I'd encourage anybody who wants to really get more in depth with this to take a look there. It's all pretty well documented. And then, so we've kind of covered a lot of what's involved with threading and multiprocessing using the concurrent future stuff. But what we've noticed over time is that there are some very important job submission settings that you may want to look into when you're running Python workloads. What we discovered, we were working with a researcher who had a Python program, and he just wasn't getting the performance that he was expecting. It said, it's running faster on my local workstation than it is on the cluster by a factor of 10 or something like that. So you're getting really, really bad performance where you shouldn't be on the cluster. And what we discovered is that when you submit with the sort of standard, okay, give me dash lowercase n, 48 cores, for example, it was not allocating the resources the way that you would expect. It was only able to spawn a single process per core, even though he was using multiprocessing. And so after looking at it and trying a number of things, we found this in tasks and CPUs per task options are really the best way, the recommended way to submit Python multiprocessing workloads to the scheduler. So it's not going to be necessarily the case for all programs or all workloads, but I think that, sort of the takeaway here is if you're not getting the performance you expect on a particular program, you might want to experiment with some of these options. Instead of using the dash capital N1 lowercase n number of cores, you might want to look into this in tasks and CPUs per task. And the way that's normally going to be done is you're going to say, really, what is the number of Python calls, Python commands that I issue in my batch script? And that's going to be equal to your number of tasks. That's normally going to be 1. And then if that particular Python command is going to do any multiprocessing within it, spin up perhaps other threads or processes, you're going to want to indicate the number of cores or threads that you actually want to use for the program. So it should be greater than 1. If you're wanting to try to do a 48 core parallel processing experiment, then you would set it to 48. In that case, you'd have in tasks 1, CPUs per task equals 48. But ultimately, what you want is the in tasks times the CPUs per task equal to the total number of cores you want to allocate. All right. Well, I feel like I've talked a lot there, and that's probably a lot to digest. But the way I usually learn best is to actually, do some hands-on and get some hands-on experience with some of this stuff. So we've got a lab, and I think at this point we're ready to begin the lab exercise. And you can get to that with any of these options. They all point to the same thing. So if you go to obby/PyLab, it should take you to a page where you can walk through the steps. We go through a section on, module loading. We go through a section on the virtual environments, and then we ultimately get into testing and experimenting with the multiprocessing stuff. So I would say, if you can, maybe go ahead and access that page. Make sure you can get to it, and we'll take a quick, 3-4 minute break just to get set up for the lab. And yeah.
All right, so we'll get started with the lab exercises. Hopefully you all have access to Easily here and logged in. So once you log into Easily, System Python is available to you by default before you load any modules. So we'll check the version of Python available to you all now. You can do a Python capital V. And as you can see, once you log on to Easily, you have Python 2.7.5 available. But Python 2.7.5 is not ideal for a lot of workloads. So I can also show you the path where that particular Python is located. Now, if you'd like a different version of Python, what you can do is module avail. And from here, you can see a selection of Python Anaconda versions in Python. And if you load, just do a module, load Python by default. It will give you the default version of Python here, which is 3.9.2. And we can check once again by typing in Python version. And you can also type in which Python. And as we can see, Python 2.7 is located here, but now we're using Python 3.9.2, which is located in tool, Python 3.9.2 bin Python here. And the which command will be a very nifty command to have, especially as we go through the lab when you want to check which actual Python version you're using. So let's also transitioning into listing available packages. So once you have the particular Python or Python Anaconda that you would like to use, you can check the list of packages by doing a pip list installed. That just might take a minute. As you can see for Python 392, these are all the packages that are currently installed system-wide for you. Now let's do a module unload Python. And let's take a look at one of the Anaconda versions here. Let's try 365. So with Python Anaconda, you can use a conda list. And that also might take a moment. All right, and these are the current packages that are installed for that particular version, Python Anaconda. Now at this point, you might wonder, what's the difference between just loading Python, such as the default Python, or should you use Anaconda? And it really depends on your workflow. Anaconda is an open source Python distribution, and they contain hundreds of data science libraries that may be beneficial for those of you who work within data science. And one particular thing that you can notice here is when I loaded Python 392, you see kind of a small list of packages here compared to that of Anaconda. Right out of the box, Anaconda offers a large amount of packages that you can use. So if there's a particular package that you're looking for, you might want to check with Python Anaconda first, just seeing the array of packages that they do offer to you. So now we can get into virtual environments and installing packages. So say by chance you load a particular version of Python or Python Anaconda, and you don't see a package that you're looking for, one thing that you could do is put in a request with our office, or you could try to install that certain package locally. Now what you could do, let's see if I can module, let me list. Me unload the Python Anaconda there, and let's load up the default Python, which is 392. Now what you could do is a pip install user and then the package name, so maybe pandas. Now if you omit this -- user, you'll tell Python or the pip package manager, I want to install this system-wide. But if you just want to install this locally to your home directory, you could just use that. But there is a better option. So say I'm working with pandas and I want to use maybe a newer version of pandas because I want to use one of their features. So maybe I want to use pandas 132, but my current workflow uses pandas maybe 120, and I don't want to mess with any of the changes of that particular environment. What you could do is create a virtual environment. So Python virtual env module, that will allow us to create encapsulated Python instances where we can perform module installations without administrative privileges, and we can avoid those software conflicts. So the virtual env feature actually creates a copy of the core binaries and libraries needed to run Python program, included in an isolated site packages location. So instead of installing it just in one directory, so that 2 versions of pandas, we'll have segmented. Each pandas will be isolated in its own site package location in your home directory. So we're going to get into virtual environments, creating virtual environments first with Python 3 and pip, and then we'll get into creating a virtual environment using Anaconda. So first, let's cd to home. Let's print exactly where we are here. And make sure that you have Python loaded. So module list, currently have Python 392. So we'll need the virtual env module in order to create the virtual environments. Now, most Python modules have this feature, but we'll just install it just in case locally here. All right. You can do a pip list installed. As you see here, we have that virtual env feature there. All right. If this command is successful, you should be able to see what files were installed by looking in the special hidden path local in your home directory here. So let's do a ls-al. And with that, for those of you who are still quite new to Linux, if you just do an ls, it'll show you all your directories here, but that al command here will list out all the hidden paths here, and we're specifically looking at this local directory here. So as you can see, we can go towards the lib, and let's go towards that Python 3.9. And this is the location where the packages will be installed there. So now let's create that virtual environment. Now that we have virtual env installed. All right, so if you can make a directory and you can name it whatever name makes sense for you. For this example, we have env1. As you can see from my home directory here, I have a virtual environment env. So you can make dir env1, and let's cd to env1. Now from here, we will create the actual virtual environment. So going back to the pandas example, I want to try the new pandas 1.2.3, 1.2.3. So I want to make a virtual environment for that. Now you all can make a virtual environment of any name of your choosing, or you could follow along with the example name there, env Python. So for me, I'll do Python 3. We're using the virtual env feature, and I'll say pandas 1, 3, 2. Let's see. There we go. All right, and that just might take a minute. All right. So now I created my virtual environment. I can cd to that. So inside your virtual environment, you'll have a bin directory, a lib directory, and this config file here. We could take a look inside of the lib directory here just to take a look. So we've created this virtual environment with Python 3.9. And this location is where all your site packages will be installed here. So as of right now, we just have the setup tools, pip, and wheel. Let's go back. And inside this bin folder, this is the folder where you want to activate that particular virtual environment. At this moment, we created the virtual environment, but we have not activated the virtual environment. So in order to activate it, you will have to use the source command. So source. And since I'm in that bin folder with this activate script, I'll just do an activate. Now, if you weren't in that particular bin folder, you'll just have to give it the full path. So let's print the full path here. So you would just do source, and then a full path to that bin/activate in order to activate it. Now you can tell that the virtual environment is activated now because you see my prompt change here. And we can also do a which Python. And now instead of pointing towards tools, Python 3.9, that Python that I'm using is pointing towards my bin folder here. So now that we have our our virtual environment activated, we can now start installing packages. So let me install that pandas so we can do a pip install pandas. And I'll just wait one moment while I was installing pandas and the dependencies there. All right, so let's do a pip listen install. And as we can see, pandas 1.3.2 and all the dependencies are listed here. And we can also check that lib folder. So now inside the lib folder, site packages, this is where all your packages are installed. Now to deactivate your virtual environment, we'll have to use the deactivate command there. And that's how you exit out. And so as you see, my prompt has changed. Instead of having the pandas there, we're back. And you can also do a which Python just to double check and make sure. So now you see we're back to using the tools Python 3.9.2 version. All right. So now we'll get into actually creating a virtual environment using Anaconda. So let me take a look at my modules here. Let's unload that Python 3.9.2. And for those of you who are new to Linux, I'm just doing a tab completion here. All right, so let's do a module, Python. You can choose whichever version of Anaconda that you prefer here. I'll use 3.7.4. Okay, so creating a virtual environment with Anaconda Python is a bit different than with using pip in Python. With pip in Python, you had to create that virtual environment directory, but Conda, it's a bit different. And let's see. So before we can create that virtual environment, we will have to export that Conda's package directory. And I'll show you why you'll need to do that if you're following along with the lab. So if I try to do a Conda create, let's say env1, you'll see you won't have the permissions to do it because it's pointing towards that tools Anaconda location. So we'll have to do an export. All right, so let's try that again. And you saw we are able to create that environment locally. All right. So in order to activate this environment, if we simply try to do a Conda activate env1, run into this problem here to where it seems like it can't find it. So we do recommend that you use source activate. And as you can see now, I'm currently using that Conda virtual environment. Another thing that you can do is, let's see if I can, let's Conda deactivate. I'm just deactivating the environment there, okay. So another thing that you could do is go inside that Conda directory and this is where your environment directory is, where all your virtual environments are stored. As you can see, I have a couple of Conda virtual environments already here. You could use that Conda activate env1. So that's just another option, but it's best to use the source activate because you can activate that from anywhere within your home directory instead of having to go into that Conda directory here, going into your virtual environments and running that command. So now that our Anaconda virtual environment is up and running, we can do a which Python just to make sure. And we can do Conda install, say pandas.
Wow, that's running right now. Oh, never mind.
Yeah. No, you can go ahead. It's probably going to take some time for that too.
Okay. Well, I was just going to say the reason that we went through the source activate and the other option for activating the Conda environment, it suggests that you use that Conda init, but we don't recommend doing that because that actually modifies your bash profile. It puts code in your bash profile, and that can lead to just some problems if you ever need to switch versions. Or you need a more dynamic environment. And so I'd recommend avoiding the Conda init. And then the other thing that was interesting is when you do the which Python, it still points to the Python binary and tools. So Conda's, I guess, a little bit different in the fact that it doesn't seem to point to an interpreter local to your home directory, but that's just an observation.
We can do a Conda list here, and it'll show all the packages located within this Conda environment 1 there. And we can see pandas. You can also use pip, I believe, to install packages within your environment, but it'll show the same here. So to exit the virtual environment for Anaconda, we just do a activate. Or Conda activate. There we go. So instead of deactivating that virtual environment env1, you'll just have to use a Conda deactivate. All right. So now we'll get into the Python concurrency and parallelism code. So there is some sample code out on tools.tutorials there. So let's cd back to home. Let's make a directory called HPC PyLab. All right, let's cd to that HPC PyLab. And let's do a copy of that tools, docs, tutorial, Python, multi. We want to grab everything in there. That's what the asterisk is for. And we want to place it in this current directory here. So let's take a listing. So y'all should have 2 Python files. So the first file that we'll work on is with multi-threading with Python. So remember, threading is recommended for programs that spend much of their time waiting for input and output operations. The code in threads.py will issue a number of HTTP requests, which will provide a good simulation of relatively slow I/O. And we'll run this job using the threads.py, using srun. So we'll run this interactively, which we do recommend. So we'll say, we'll take 1 node, 1 processor, and we want to use the bin bash for the shell. And for Hopper users, this is where the lab exercise is more tailored for easily. As you can see, the scheduler looks a bit different from the schedule that you're using on Hopper and the command for running an interactive job. So, all right. And okay, yes, someone put in the chat for Hopper the command. Let's do a module list. Okay, I have must learn. Let's do it as one. And let me just try some reason.
Yeah, that's odd.
Yeah, let's try this. You know what? Let me exit out and see if I can. There we go. Let's list. Yeah, I could have just need to clear my. There we go. All right, so go back to the HPC PyLab. And as you can see, I am dropped out onto node 36 here. So we can run this job interactively. And let's load up Python. So module load Python, which will give me Python 392, which is the default Python. Let's do Python threads.py. Let's just try with one. All right, and as you can see, the execution time took about 3 seconds there. So let's increase that thread count to 4. And you can see increasing that thread count to 4 significantly gave us better results there. Let's try 8. All right. And let me exit. So we'll get into the multiprocessing with Python. So that particular exercise, we were working with threading for IO specific task. So now we're getting into CPU bound workloads like math operations, where we can use parallel processing instead of threads. So first, make sure that you exit off of that node. And let's resubmit using in-task and CPUs per task, as Bradley pointed out in the slides earlier. So let's do an srun. So let's say we just want one task. Amount of CPUs per task, we'll say, let's do 8. And we'll use bash as the shell. As you can see, it dropped me out on node 58 fairly quickly. Let me print which directory I'm in here. Let me cd to the, let's see.
I know what that is. Give me 1 second, I'll correct.
Okay. Here, I'll cancel out there. See if I'll do that. All right. So this particular lab, let's take a look at it here, procs.py. And we're using the concurrent futures in order to do the parallelism here. And while we're waiting, I'll also show you the thread script here. For the thread scripts, you'll use the concurrent futures, and you also import threading. All right, so we will.
Raina, the quick fix would be I pasted a command in the chat that might get it going. I think temp might be full. We've been having a problem with that.
Okay. Want me to try another?
I think it's gonna, unless you could specify a node, but it's up to you, however you want to approach it.
Okay. Yeah, I can try another, just to get some practice here.
For anyone else that might be encountering that error in their, while they're working, you could try that export tempdir equals /local. And I'll try to clean up temp while I do.
Okay, let's see. Oh, is there a specific node you think would work? We can probably do, let's see what's open and available here. Have any HPC? Okay, 131, let me try that one. Let's see, what was it, W node. Let's see, 131. All right. Let's go back to the HPC Pi Lab. And Bradley, was there anything you wanted to say before I run this script about the procs and the thread? Just taking a look inside the.
No, the main difference is in this case, you're doing a math operation with the function to determine whether a number is a prime number or not. And the other one was basically just pulling web content. So it's the main difference is IO bound versus CPU bound.
All right. And I'll make sure. Let's load that Python module. Let's do a Python procs py. Let's just try for one. We'll give that some time to complete. Right, that took around 21 seconds. Let's increase the amount of cores to 4. Let's sped it up a bit. All right, so we went from 21 to 6. Let's increase the core count to 8. And that cut the time down to 3. So in the last section, to demonstrate the importance of job submission parameters, let's try running the procs py program again, using the more standard node and core allocations. So for this particular lab, we use the CPUs per task and in task. But now let's just try with, exit that. Try with standard format here. All right, and let's run that procs.py once more, just to see if there's a bit of a difference. So we'll start out with 1 core. as you can see, it took about around the same time. Let's increase it to 8. All right. So as you can see, the execution time was a bit similar with the in task and CPU per task. It seemed once you selected the count of 8, it was around 3 seconds. So you can use either format, but you may want to try both to see which works best for your performance. But either should work fine for you all. But as a general guideline, we do recommend using in task and CPUs per task. You may get a slight better performance, but it still comes down to your workflow and what works best for y'all. So, and that is the end of the labs. If there's any additional comments any of the other admins would like to add there.
Yeah, just to reiterate, that last part was really to demonstrate that with the wrong job submission parameters, you don't get any performance improvements. As a matter of fact, it looked like it was even a little bit slower. The execution time was the same, but there's overhead. If it's actually trying to spin up processes, there's a little bit of overhead involved there. So, it's real important to make sure you're using the right job submission parameters, and that just may be a matter of trial and error. Running interactive jobs, testing the performance of your code, and then adjusting the parameters to see what's the most optimal allocation. But yeah, I think that kind of brings us to the end of that presentation on Python for research computing. Obviously, it's difficult to be really comprehensive there, but hopefully that highlighted some of the main points and maybe gave some folks some ideas of how they might improve their workflow. I will say some of that was involved for more for people who are actually developing their own Python code. If you're using existing Python code, you may want to just look and see in whatever documentation, does it use threading? Does it use multiprocessing? And see if you can take advantage of any potential performance gains you might get from those. And again, that's sometimes just a matter of trial and error and testing to make sure, or if you have some kind of benchmark or sample input to use that runs relatively quickly, you can get a good idea pretty easily of whether or not those your job submission parameters are working as expected, and hopefully get some good speed up there, because the reason for using an HPC cluster and going through all this pain is so that you can get faster answers to your questions. And hopefully this presentation may have given some folks some ideas or some further insight into it. And if you have questions or you see some things that just don't make sense to you, let us know and we'll do our best to help. I think at this point, we can open it up for just questions. We got about 15 minutes left on the advertised time.